this week we talk about dimensionality reduction. So again, the first question is to help you to understand what is dimension reduction. What is the motivation of dimension reduction? So my first question is, what does this dimension mean? In week 1, we talk about a lot of dimension, non-p dimension, non-pi dimension. You define a non-pi array, then you define a dimension. That dimension is number of rows, the row is one dimension, column is one dimension. So normally in this unit, you deal with two-dimensional array. But if we add an inner bracket, inner square bracket, so it make it into 3 dimension, right? I think you still remember this material in week 1. But we also talk about data dimensions. Anyone remember what's the data dimension?
Would the data dimension be like the number of features and the number of attributes?
Yep, correct. So that will be the dimension we are talking about today. Is the number of attributes, number of features. So why we want to reduce the number of features? This is another question.
I guess if we reduce like the dimensionality, we can kind of visualize, or we can apply like machine learning algorithms to it. Yeah.
Why you don't say visualize?
Well, I was gonna say visualize just because I was thinking of the graphs that I've been making. But is it better for certain algorithms? I guess it also means that we can see it too.
Yeah. Your answer is accurate and all correct. First answer is first motivation is for visualization. We may have a 5-dimensional data, so that means we have 5 features. But all we can do is visualize, features on a plane. So maybe we can visualize in the planes. You draw plane in a 3D dimension, you still can visualize it. But more than 3D dimensions, you can't visualize it. So that's one reason. And another reason Mitchell talked about is for certain machine learning algorithm. I really like your words. It's very precise. For certain, it's not all machine learning algorithms. For certain machine learning algorithms, if you reduce dimension, it will be beneficial. But for all, one perspective is like it will be computational, safe computations. Is because you don't have so much features to process. All the machine learning algorithms need to process all the data you give to them, right? So for all the machine learning algorithm, it can save computations. But for certain machine learning algorithm, it will be more, maybe more accurate. Why? Why for, don't talk about computation. Talk about other perspective for certain machine learning algorithms. Anyone know why? One hint is, I think that Margaret says something else. Let me go through that later. One hint I can give to you is why does dimensionality reduction will benefit certain machine learning algorithm in some other perspective? One hint is distance-based machine learning algorithms, like we learned last week, k-means algorithms. What's the problem if you have many dimensions? What's the potential problem for this distance-based machine learning algorithm if you have many dimensions, many features, maybe 10,000 of features? Yes.
We have multiple features, but they are somehow distinguished. Like we have 4 categories, and for each category we have multiple features, but they are representing only single categories. So in terms of a cluster and data, So they are providing a kind of similar information. So by reducing the dimension, we are basically uh, like reducing multiple feature into a single, that would be much more easier to understand and even the visualization.
Yeah, I think
Like
you.
because they are pointing out the similar information.
Yeah, I think you talk about the correlation between features. That's another point, another very, very important point to do dimension reductions. It's also why we can do dimension reductions. It is because actually we don't need so much information to do them to train a machine learning models. I will give you a concrete examples, but I think no one answered my question. Is like for some like certain machine learning algorithms, like deep distance-based machine learning algorithm, why reduced dimensionality will be beneficial. My answer is it's because of dimensionality. I think I mentioned it in previous weeks. I don't remember, but anyone know what's the curse of dimensionality? If you look at Claudican content, you should know that. Anyone still remember that?
Yeah, I think from my memory, curse of dimensionality, if the feature is growing exponential, it's become so complex and is growing so fast. So that's from what I remember. So actually, in simplify, it add complexity and from my memory, overfitting as well. That's impact the performance.
I don't think it will make model overfitting. I'm not sure. I will recheck. I don't think it will make model overfit. The thing is when you have a many dimensionality, the volume of the space will be increased. Put it in a simple example. Let's say maybe you and me. The distance between you and me is 1 kilogram, 1 kilometer, right? So this is in 3D space, right? Because we live in 3D space. But if we are Superman, we live in 4D space, 5D space. You will find the distance between you and me will be increased. It may be 100, not 100, but maybe 3 kilometers. So, yeah. So that will be the problem. Why?
Yeah. Sorry,
Because
I did a quick search just to see if there is any correlation for overfitting with curse of dimensionality. Yes, mentioned many times. I remember that because I was searching it on the last report. But yeah, to your point, I think it's become more complex because we have a lot of dimension and a lot of data, a lot of features.
Will that lead to overfitting?
Yes, there is a lot of papers speak about that increase the risk of overfitting. It's not mandatory to become overfitting.
Yeah. So one interpretation for that is that you see your distance, the distance between, before we have too many dimensionality, the distance between a group is very, very dense. So the group can be identified as a group. So you guys can be identified as group of machine learning students. But if your distance distances between you become very, very big, so it will be sparse, So in that case, you may not be identified as a group. Although actually you have similar properties, you are all machine learning students, right? So in that case, you can relate to the overfitting because the models is hard to identify such groups. So it identifies each people, each person, each of you as one group, as one. So you say that will be overfitting. What overfitting mean is it will bias toward individual data point of certain perspectives to focus on small thing rather than the generalizable features, generalizable properties or groups. So that's one interpretation. Oh, thank you, Ahmad. I will have a look later. Let me. Oh yeah, data sparsity and concentration effect. I think that's what I'm talking about. That's great. And let me look at I think Margaret said something. Yeah, remove the redundancy and this is related to, I think before who talked about Asin. I think Asin just left this workshop. He talked about this. Yeah, that's correct. Some correlation between features. Yeah, okay. So I think we have enough motivations for doing dimensionality reduction. We have visualization, as Michelle talked about. We have correlation, decorrelation motivation, as Margaret and Ashin talk about. And I think, and curse of dimensionality. And Amma talked about the overfitting. Yeah, because curse of dimensionality also lead to overfitting. As Cam talked about, data sparsity and concentration effect. Oh, good. So now we need to find the methods to do dimension reductions. I have a very interesting example just for you because I asked this question in all the workshops, the answer is the same. So I want to try this workshop. My answer is we have a data set about people. Each data point is one person. So this data set have two columns, two features, two dimensions. One dimension is weight, another dimension is height. So I have height and weight of persons. So if I want to reduce weight and height into one features, how will you do? Any solution for that? All the answers from all the workshop are same, so I want to try this workshop. No answer? Reduce height and weight into one feature. Oh, SVD. That's too much. Actually, I won't talk about SVD today. You don't need the SVD to do your assignment. Yep, we are engineering a new feature.
Like we can calculate the ratio of weight and height.
Yep.
Like we do in fitness gym, they calculate the BMI according to the weight and height kind of.
Yeah, the ratio, the BMI. Yeah, the BMI is a key word. Actually, all the students at all the workshops, the answer is BMI. So correct. But this is really interesting test. But actually, BMI is only used for height and weight. But we want to have a generalizable, criteria process. BMI is one function. This function is specific for weight and height. Do we have some other, generalizable process for different, different data sets for any data size? Someone say PCA, Margaret say PCA. Before we're talking about PCA, anyone know what's the underlying concept, to reduce the, let me see in this way. When we use PCA to reduce dimensions, let's say two features to one features, what we want to maintain in this two original representation with two features? What's the underlying concept? What's the underlying idea when we do such, transformation?
I reckon we need to understand or get correlation between the variance, where is the feature actually has the data. So and the drop feature, which is has low it's not that important, so it's not impacting the data by much.
Wait, you got the, oh, Margaret also got the point. Yeah, this workshop is full of smart people. Actually, I haven't got the answers from the last 4 workshops I just conducted this week. Yeah, the thing is variance. Then someone, I think Baron. Oh, I love the Baron's answer, but actually it's not the answer for my question. But I love your, this engineering thinking. This is down to earth thinking. You talk about the vector dot product of 2 vectors. Oh my God, this is so good. This is you already answered some question I want to ask later. So great. But yeah, go
And
for
just
variance.
like point,
Yep, please.
before variance, do we need to change the scaling also, scale of the 2 different features so that it could be in the same scale?
Oh my God, another good question. Yeah, the one actually I also talk with Margaret and Mitchell in Health Hub session. Yeah, should we scale the data before we calculate variance? Is that your question, Asim?
Yes.
Yeah.
Like, because
Yep.
2 feature could be have different scales, so I was assuming like first we bring the scale, similar scale, and then calculate the spread of the data and calculate the variance and everything.
Yeah, but when we scale the data, what is important, as you say, is the spread of the data, is the spread of the feature, is the variance of the feature. If we scale this data, the variance, the spread of the feature will also be changed, right? Asim, do you agree with me?
But like depends like which scaling features, like let's assume like in case of min max, we are just scaling down the feature, but the spread is similar, distribution is same.
Yep. How about standard deviation, Asim? If we use standard deviation, what do you think? I mean, the standardization will subtract mean and divide by standard deviation.
For the for Z-score deviation, like I do not like see. I think we are squish the data in a cube for the maybe in case of standard deviation we could change the spread. There could be chance. I'm not sure.
Thank you for the honest answer. Yeah. I think correct before he said the min max won't change the scale. Actually, it will change the scale, but I think what I want to emphasize is that it won't change the the spread when you compare the normalized feature 1 and feature B. Actually, the relative spreads are maintained, right? Is your claim right, I think?
Yes.
Yeah, I think actually I haven't tested it but I think according to mathematical property, I think it should be correct. But maybe I need to have a further look. But I'm very, very 100% sure that if you use standardization, if you subtract mean and divide by standard deviation, then you will change the, even the relative variation will be changed, relative spread will be changed. So don't do that in your assignment. I can't say don't do that, but if you do that, please give me give me the reason. Otherwise, I think it's not good practice. It will just ruin the good things in the future because you change the spread of the feature. Great. So we talk about spread, we talk about variance, but I think I will hope to give all the people intuitive understanding why spread is important. What's the spread? How spreads relates to the variance? Where is my? Yeah, here's my GitHub link. Let me go to dimension reduction and go to this pose. Another pose I wrote for this unit. Okay. Actually, I just add some comment for correlation. Margaret talked about correlation before. I think also talked about correlation. Yeah, here is same example as last week. But rows and columns are reverted. The rows is documents. The column is words of good and super appear in the documents. How many times these words appear in the documents? So if you can see this document is positive, so I see 5 times good appear. So do I need to see appearance of super to know this is positive? No, because good has already appeared. So I don't need to see the second feature. I only need to see the first feature, right? So that's a correlation. That's a redundancy Margaret mentioned. Before I go forward, let me see. Yeah, okay, no question. Clear, right? This is redundancy. This is the correlation of features. And then we go back to variation and the variance. I want to show this example. I think I tried this example in a lot of workshops. They think this is interesting. Okay, so I just use this example. This example is for the for Hangouts with friend A and friend B. Each column represents one friend. You have 2 friends, friend A and friend B, and each rows represents the Hangouts with each person. Let's see, your friend A hang out with you twice this week. Your friend B hang out with you 4 times this week, and this is a hangout with other person, hangout with another person. So clear with this data, right? Let me have a look. Any question? Nope. So I think everyone clear with this data. So my question is, if I want to have one column, I want to look at one friend. If I look at this friend, it can tell me some patterns about the data. Let's say something like, oh, whether that point this person is a very outgoing person who always want to go to the party. Whether another person is like introverted person, always like stay at home, something like that. So which feature you want to look at to find this pattern? I want to hear your answer. Something like this, because this is hard. Okay. A. Margaret, why A?
Because I think like I sum them up, 10 plus 20 plus 2, 32. So like the A person, right? They were willing to hang out with people, so it's more friendly.
Yep.
Compared to friend B total only like 9. So yeah, that's my reason.
But what I want to look at is that point. You know, the rows are that point. I want to find the pattern of that point. My question is, I want to select a feature. If I select this feature, I don't care about another feature. So, you know, if I select A, I don't care about what B represents. So I only look at A. Then I can identify some patterns for this. For me, for person 1, for person 2, for person 3, 4. If I have a new person, it can it can identify very well for, whether another person is a maybe introverted person, or another person is a outgoing person. By by looking at the handout record for friend A or friend B. let me make the question simple. If I want, now I have a 3 person, right? Now I want to look at a new person. I want to know if this new person is outgoing and introverted. Now I only give you a chance to look at one values. The value is the hangout times with friend A or the hangout times with friend B. Which one you will choose? Which value you will choose to determine the new person, whether this new person is outgoing person or introverted person. Ama, why B?
Yeah, just in my opinion, when I look in E, I see a bit impulsive. So he put 2 and then 10 and 20. So the gap is quite big. So I'm not sure the data here is more accurate. So maybe has opinion, but I think friend B quite modest.
It's accurate. Okay, and Lin Mo answer. I want to hear any different answer.
I guess you'd probably want to hang out with friend B because you hang out with them twice as much as friend A. No.
Much twice as friend 8. What do you mean? Much? Can you clarify?
Yeah. So I guess in the top line there, where you've got friend A and friend B.
Yep.
You've for yours there's a value of 4 for friend B and a value of 2 for friend A.
Yep.
So it seems like you're like hanging out with friend B more. No.
Hang out with friend B more, but actually I don't care about these 3 person now. I just want you look at these 3 3 lines. I want to let you choose one friend. If this friend will better indicate whether new person will be outgoing or introverted.
Right. My bad.
No, I know it's not clear. I think because this question is very important, it's very important for you to understanding the whole story of PCA. So that's why I want to make sure, because it's about the spread of the data. Before we talk about in theory, we always want the spread of data. The feature with the most spread of with the most spreads is good, right? We want to choose that. So it's more. It gives us more information, but why? So that's why I want you to understand this. I just want to try. Let's see. Now it's 42. Okay, before 43, let's see if there exists any more answer. If no, I just give you my insight. Just any idea. Actually, it's open. No correct and wrong answer. I just want to hear your idea. Maybe just not on the point of the today's story, but yeah. But I want to hear anything. Okay. So I just give you my my story. My story to align with these things. What's the idea of PCA? You may already know the key idea is a spread is variance. We want to find a feature maintaining the most spread and most variance. Why? As you can see, this one has more spread, right? You don't have the problem with that, right? Make sure if you have problem, just tell me. We can have a discussion. Feature 1, friend A will give more spreads on the whole data. All good? So next question is, why the most spread of data will benefit to find the general patterns in the data? Would be good to represent the whole data. So that's the question, very important for PCA. The answer is, you see, when you have a new people go in, you want to look at value of, maybe look at value of friend B, how many times this new person hang out with friend B. Maybe the answer may be 3, 2, 4, 5 of 2. It's in the very smaller range, right? So you can't tell whether this value can indicate this person is, maybe it's 5. 5 is large, right? But it's not compared to these 3 values. It's not like have big difference. So you maybe not so confident that, okay, this value is outgoing person. But if this, let's say the range is very, very different. Let's say if this is outgoing person, there is likely that friend A will go with him maybe 15 times, right? So you can be confident that this is outgoing person, because the range of the possibility to go out with friend A is very, very large. It has large range, So if the value is large, you can be sure that he's the outgoing person, not like this friend B, okay? Because the change will be amplified across the spread. If there's more variance, make it more obvious. I think make it more obvious if you are working with the integer and not the float. Yeah. But why you, Baron, you said if you are working with integer, not float, what's the problem with float? Hello, Baron, what's the problem with float here? I'm not sure what you are indicating. You mute yourself, Baron. If they are not great, yeah, correct. Noise. Yeah, you are correct. Yeah. That's the problem, another problem of small values, right? Small range of values with not big variation. You say even the loss of the fine details, go with the, precision of the number of floating number maybe affect the result. But for the, for friend A, it doesn't matter, right? Even, the floating point will affect the results, but the range is big enough, the difference is big enough, even though it will affect result by 1 and 2. That's okay. I still can get the, the value will still be big enough for me to identify this person is outgoing or not outgoing, right? Everyone clear? I hope you are clear here. Yep, I think everyone's clear here. So we have conclusion that we want the feature to have more spread, to have more varied values. No. So Baron, nothing about this. Oh, sorry, statistical different. We just save this. I'm not sure what you are specifically mentioned for statistical significance. Small spread. Yes, the variance does relate to the statistical significance, but just put it aside because that's too far away from today's topic. If you're interested, we can have a discussion later. Great. Yeah, so how to measure this variation? This is a problem. So I don't want to just to ask this because all of you know we use variance, right? But I hope you know why variance can measure this variation. The variance, the differences of data points, differences of all the values for one feature from its mean. Okay, so I hopefully then multiply them together. Then you average them. Okay, so that's the thing. If this data is more spread, the mean the each data point from the mean will be very big, will be large, right? So you sum of these square differences of the square differences from the mean. So it also will be very large. You put square for the difference, it will amplify these differences, right? So that's why we use variance. So okay, now I want to make a claim here. Feature with greater variance often have a more predictive power. So what we want is we want to the feature maximizing the variance. My another question is, why not we just selecting one feature with the largest variance? Let's see for this example, if I measure the variance, the super has a larger variance. Why not I just choose this super feature? Just get rid of this good feature, so I reduce 2 dimension into 1 dimension. In that case, we don't need to PCA. We don't need PCA, right? We don't need to do some complicated thing. Like the p-value and whatever the likelihood that the change is caused by intervention. I have to review some statistic. Yes, I think I haven't been used p-value for a long time, so I forgot what the underlying how it works. So I have to go over it to answer if it's the thing. So yeah, but good to think about this. I love to correlate things with other things that will enhance our memory. So we have a big knowledge structure. Yep. So my question is, why not we just choose this super feature? What's the drawback to choose just this super feature? To choose just this feature? Let's have a have a little bit thinking. Super has larger variance, so more variation. If I choose super, what information will we lose?
So see,
yep.
So see, let us assume if we take only the super feature. So if we consider like first two case D1, D2, it's a 0, 0. So let us assume we order it 0 to be the high number. But if we use the combination of the two features, then we get the more appropriate priority order. Like already you have mentioned, like D1 is neutral, D2 which in the super is similar 0, but along combination with the second feature it's a moderately positive. So we change the meaning of the information if we use the two features, not a single feature. So if we consider only one array, then it will be 0, 0. But if we use with the good feature another vector, then the semantics is changed.
Yep.
About the.
Yep, correct. So let me make a simple, make it simple. Just focus on this feature, this data point. If we only use super, we can say it's 0. So we may think of it as neutral and negative review. But if you have the information of good, you will know this is positive, right? So this is the reason why we want to consider both feature. doing the dimensionality reduction, we want to consider both feature into one feature. Transform both feature into one feature. Transform transform these two value into another value. That's the thing. That's what the dot product want to do. How to do that? Actually, Baron already give the give the down to earth answer. How to do that? We do that by using dot product. We find another vector that has two values, then dot product by these two features. We dot product this vector by each data point. So we get the one features for all the data point, right? So, but as I said before, we need to make this transform feature maximizing variance. This is a key thing we need to do. This is why we need the PCA. Okay, so our goal is we need to maximize. We need to find vector to do dot product with the original features to get new feature, which will maximize the variance. Okay. Now we already know how to use variance to calculate the variation of single feature, but you have whole data sets. You have a different feature. The spread of data is not represented by variation of each feature separately. It has a correlation between feature. If you want to measure the whole spread of data, you need to think about this correlation. So let's introduce another measurement called covariance. So before I talk about the covariance, anyone can tell me what's the formula for covariance? Actually, I already talked about the formula for variance. The formula for variance is maybe we have a value that point 1 D1 of feature 1. Feature 1 have a 1, 2, 3, 4 values. Then we minus by mean of feature 1. Then we do the square, right? Then we divided by the number of example, that's n. This is a feature 1. Anyone can give me the equation, the formula of covariance. This is the formula for variance, right? What's the formula for covariance? Covariance need to care about two features, feature 1 and feature 2. If I let you to design a covariance, here is variance. I let you to design a metric for measure the spread of two features. What is your solution? What is your formula? By the way, here is a feature 1. It has maybe 4 values. So you think about it as vector. You minus 1 scalar value. You also get a vector, right? So if you have a vector, you put a vector to do the square. You may think you got the 4 values. So don't think about it in that way. Actually, what I want to do here is I want to you can think about as a dot product. In that way, I will just square each values, and then I make a summation of all of them. Make summation over all of them. But it doesn't matter, right? You can get the general, equation of the variance. Any idea to decide the covariance? Yep, please, Amma.
The meaning, just the difference from the mean value. That's what I remember.
The difference from the mean value. Yeah, also always care about the difference from mean value.
So you need to calculate the difference for the mean value for function 1 and function 2.
Yep.
And then some sort of normalization after that, divided by something.
Yep, great. Let me expand this. This square equal to what? This square actually equal to, I make a multiplication, right? So now we have two features. How about we just do this? Then, this is a general formula. Why we want to do this? Because if you make F1 equal to F2, then it will go back to this formula, right? So actually covariance is a general form of variance. So yeah, do you think this is a unified version? Actually, every time I see some formula with a unified version, I feel very happy because the world become clean. Bayesian inference. Bayesian inference is very big topic. What do you mention? What kind of thing you want to mention, Baron, for Bayesian inference? Just type something. I will wait for you. Before waiting for you, I will go further. So Norris, you can take your time.